So let's do this for something where, like in the homework problem, you have average conditions, or you're looking at an entire device. So the previous slide, we were saying, okay, that's going to end up being a function of x. That gives us like a local value, a local friction coefficient. What if we want to do something similar for the average condition? How would that look? So let's look at our definition of shear stress, average shear stress, so tau s. If I want to take the average of that, that's going to be just simply the integral divided by the length, so from 0 to L of tau s dx. Just a length average integral there. So we take that, and then we're going to non-dimensionalize it again using what we had from the previous slide. So that becomes mu u infinity over L integral from 0 to something. I'll come back to that. Partial u tilde with respect to y, evaluated at y tilde equals 0 dx. So we're now integrating this thing from, we were integrating from 0 to L, but once we've non-dimensionalized it, what do we have to integrate from? 0 to 1, right? Because that's going to be the full extent. Okay, so we're writing this out for our average shear stress condition. Okay, so then translating this to average friction coefficient, C bar F, that becomes 2 over rho u infinity squared, mu times u infinity over L, and then this integral 0 to 1 of partial u with respect to y at y equals 0 times dx. Oh, by the way, it's dx tilde, because once we normalize it, it goes from 0 to 1. So dx tilde. Okay, so that's the average definition, so we got to keep going with this. What do we notice? So from this relationship, I'm going to say C bar F is equal to C bar F of what? So using this relationship, I can now decide what my correlation has to be a function of. So again, we're going to see a Reynolds number kind of shows up here. We're taking an integral over x. So in the end, this is a definite integral. Right? We're going from 0 to 1. We can evaluate out anything that has to do with x. It'll go away. It's like accounted for in the integral. Y is evaluated at 0. So my friction coefficient average value is not going to be a function of x or y. Right? That's just going to be a function of Reynolds and of dp dx tilde. Okay? So, prior to this, what you'd be given is something like, okay, here's my local correlation. You see what goes into the local correlation. You're given an average, but you never really know why certain stuff is included. This high-level analysis is really what tells you what should be included there. Okay.
The local friction coefficient is using the Reynolds number at location L instead of x.
The local is going to be using Reynolds number evaluated at, if it's a plate, it would be at x.
Right. So should that be already set x for the local?
Let's see. Look back at that.
Because we non-dimensionalized it.
Right, yeah. REX. That is a good question. Let me come back to that. I'll look into it. You could be right there. It might just be notation problem on my part. I'll look into that, but I think the Reynolds number would be, if it's local, it's going to be evaluated at the characteristic length, which would be x for that local position, right? If this is for flow over a flat plate. If it's not flow over a flat plate, then it would be whatever the characteristic is for something else, whatever that other thing is. So I'll get back to you on that. All right, so let's look at an example. Again, like you probably have seen correlations before, but just it's been a while, you kind of don't remember what it looks like. The idea is that, okay, we have the relationship. This is what? So this is flow over a sphere. So the characteristic length for flow over a sphere is the diameter, I guess. So for this correlation, you have the Reynolds number that you compute based on the diameter. You have the pressure gradient, which is, again, something that's probably going to be given to us, or we just assume is small. So you end up with this like average friction coefficient, which is just a function of Reynolds number for our given shape. What this would look like is you would have a curve that you develop. You take data. All right, so this is our data for measuring what? Drag coefficient is a function of Reynolds number, and then you just sort of fit the best curve to this that matches the data. This is exactly what you're trying to do on the homework, is you're taking experimental data, right, experimental data, and you are backing out of that data the right coefficients that go with a correlation that's functionally dependent on the stuff you care about, which would be Reynolds number. The Nusselt number is what you're predicting. You need to know Prandtl number. That should be it, right? So this is kind of how it would look. One thing that for this particular correlation and something you'll need moving forward is we've talked so far about friction coefficient. Friction coefficient is related to the shear stress. So if you know friction coefficient, you need to know something about the total area that's exposed, because the friction coefficient relates to shear stress, which is going to be related to force by way of area. If you have something like a flow over a sphere or flow over a cylinder or something where it's like an external flow over some object, often that is captured in terms of drag coefficient. And drag coefficient is really similar. It is looking at the drag force divided by the momentum. But the difference here is instead of the area being like exposed surface area, the definition of the drag coefficient is the projected area, so A sub P. So for this example, the projected area would be this, this disk. So looking head on, it would be, like a disk of the sphere where flow is in this direction, and this has some, radius r. So really the only difference between the friction coefficient, the drag coefficient, is the definition of the area here. And maybe a factor of 2 involved. Okay, questions on the correlations part? Okay. All right, so yeah, again, just to kind of wrap that up and say it again, the goal of the correlations is to determine functional relationships. Once you have that, then you just have to decide what the equation looks like, and then you come up with probably a fit to data to get it to work. All right? But the really powerful thing, and I guess the point of this and the cool thing about it is, like, what you have is a relationship that doesn't care at all about the actual geometry, like the size of your thing. It's all normalized in terms of like Reynolds number, these non-dimensional parameters that are fluid independent, they're geometry independent, they're temperature independent. I mean, they don't really, they don't directly account for that stuff. It all is like rolled into the dimensionless numbers. So you can collapse all the behaviors down to one curve and then back it out after the fact, right? So that's the really powerful thing about doing correlations this way. Let's see, I think I had an example for the energy equation. Yeah, I'm just going to go through this really quickly because I want to get to the next part. But for energy equation, let's say we have this goal of, again, getting a correlation. What we want is to get, let's say, heat transfer coefficient. So I'd use Newton's law of cooling. Q dot double prime is equal to H times T S minus T infinity. So I want to develop a correlation that I can use to predict the heat transfer coefficient H. So I'm going to solve for this. H is equal to Q dot double prime over Ts minus T infinity. using Fourier's law, q dot double prime equals minus k partial t with respect to y, evaluated at y equals 0, because we're looking at conduction across the boundary layer in the y direction. So using that definition of Fourier's law, substitute that into my h equation, and I get h is equal to minus k over ts minus t infinity times partial t with respect to y at y equals 0. So then I can go through and sub in my non-dimensional values for temperature, which is theta, and y, which is y tilde. And I would then get this relationship. So that becomes minus k over ts minus t infinity times partial of theta tilde, which is then times t infinity minus ts divided by partial of y tilde L. And then all of that is evaluated at y equals 0. A little small over there. This can be simplified down. So what I guess look at here, we have ts minus t infinity minus ts. So I could pull out the t infinity minus ts and flip it around. That minus out in front here, this minus out here, would go away. And those are constant, right? They'll cancel. So then I'm just left with this kind of simplified equation, which is h is equal to k over L partial of theta with respect to y, evaluated at y equals 0. Okay, we can also use the definition Nusselt. Nusselt is equal to h times my length over k. And then what I would observe by relating these two things together is that Nusselt is actually equal to partial theta with respect to y, evaluated at y equals 0. Okay, so all of that math was just to get this dependence. So now I'm going to develop a correlation in terms of Nusselt number. I know what I have to look for in terms of functional dependence. So this doesn't depend on y because we're evaluating at y equals 0. What it does depend on is theta and anything that theta depends on. The other thing to notice here, by the way, is the Nusselt number is actually a measure of the non-dimensional temperature gradient at the surface. Right? It's kind of an interesting conclusion that comes out of this. So based on this, I would say my Nusselt number is, squeeze this down here. So Nusselt number is a function of x, Reynolds number, dp dx, and the Prandtl number, and the Eckert number. Because we have to look at all the stuff that theta depends on. It's kind of all that stuff. All right, so your correlations that you're going to develop are going to maybe have to account for all that stuff. For an average condition, I guess I've kind of run out of space, but for average condition, the x part goes away. For flows where viscous dissipation isn't important, the Eckert part goes away. So in a lot of cases, what you end up with is Nusselt number is a function of Reynolds number, Prandtl number, and then you'd have to be given or assume something about the pressure gradient. Okay. An example of this would be flow over a cylinder. So in this correlation, what you see is a relationship between the Nusselt number and Reynolds number. So that's the first dimension we care about. Here, viscous dissipation is not important. But you do see these different curves that show up for different Prandtl numbers. So there's a functional dependence on Prandtl Reynolds, and then dp dx for this cylinder would be given to us. Okay, so that's as far as we'll go on correlations. Again, in the homework, you're just kind of using these concepts to develop a relationship. I give you the function that you have to fit to, so your job is to figure out how to relate the dimensional stuff to non-dimensional quantities, take the data, and then fit to that. So what we'll talk about here is something called the integral method. With our boundary